Okay, so our last review for the last quiz, and this is the material from the since we went online. So these are these 4 chapters here. So here in you have a much better way of preparing for this test in some sense, because you have all these videos that you can go look over again, check as much as you want. Especially the review videos should be very useful. Another thing you definitely have to do is look at, especially when you did mistakes in your quizzes, go look at the solution videos to see what the mistakes were that you made. Okay, so all this material is available, and you can go back as many times as you want, and you have to kind of prepare yourself. Don't wait until the actual quiz to go look at the reviews, because it's too much. You don't have the time. I'm giving you 3 hours, but many of you took almost an hour and the whole class time to just finish one question. Now we have 4 questions. Okay. So I picked out here what I would say the topics that I might ask a question about. I'm not saying all of them, of course, because they're going to be 4 questions only. So let's quickly go over everything a little bit, and then we do some review, because some of the things I'll refer you to other review material. Well, first of all, we did determinants, and we have 2 ways of calculating determinant. So the original way was the row-column expansion, and then we saw that somehow more elegant or quicker way sometimes was via row reduction. Now, both methods are very important, and because in the rest of the questions, very often you have to calculate determinants, and it's not that just everything, you cannot just do one method, because this row reduction method involves very often row reduce, and then at some point you start expanding along a column and a row, namely a column of row with a lot of zeros, well, basically all zeros except for 1, and so on. So both techniques are actually combined in one single technique, which you have to master. So determinants are going to be a lot of questions, so I'm not even sure that I will ask you to a direct question on determinants, because you're going to have to do so many determinants anyway. Now, using determinants, we have talked about the inverse of a matrix via adjoints. We had another technique that you had tested in the previous quiz about just using row reduction. Now, this is again a topic in chapters 4, 5, and 6. You're going to have to find inverse. I mean, chapters 5 especially, you're going to have to find an inverse of a matrix. So you have the option which one to use. Now, I want to point this out, and I will review a little bit this adjoints. I see some of you have used that to calculate an inverse, but you basically just write down that's the adjoint. Now, that is not acceptable on the test. If you want to calculate an inverse of a matrix using adjoints, I have to see all the details. And I'll explain what I mean with all the details. I'll do it an example. Okay? So you cannot just write down this is the adjoint, and therefore this is the inverse. Okay? You have to show all the work, all the steps. There's also an application of determinants where we can solve a similar equation using Cranmer's rule. It's a very time-consuming calculate. It's a lot of calculations, but I'll show you a little example of how I might ask you to do this. Okay. Then chapter 4, basis of column, row, null space of matrix. We have discussed this, and in fact, for this one, I have made already a review video. This was the let's see, that was the video in session S20 in the 26th session. So go look at session 26 for the review video there on this. So you have a full review on that. Then the basis of eigenspaces, we've done this now many times. So again, I'm not going to really review this particular topic. We talked then about diagonalization, orthogonal diagonalization. I'll say a little bit what's the difference and what's going on here. And then the last application we did was quadratic forms. Okay, so let me go over some of these things. So first of all, I want to talk about the inverse of a matrix. As I said, it's a topic that you're going to have to deal with, whether it's asked explicitly or not. You're going to at some point have to find an inverse of a matrix, even if I don't ask you explicitly, but I might ask you this, for instance, in this part. Okay, so the inverse of a matrix. So I want to actually show you the advantage, disadvantage of the methods that you have. So we have 2 methods, right? We have the method of row reduction, and we have the method of adjoint. And now let me do this on a simple example here. The matrix I have in mind is 1, 0, 3, 0, 2, 1, 1, 0, 0. Okay, and if we would do this row reduction method, then we have done this now in the previous quiz, right? So that was, we have to, okay, let's do this quickly. I'm going to write the row operations here. I'm doing row 3 minus row 1 to get 0 at the bottom. So get 1, 0, 3, 1, 0, 0, 0, 2, 1, 0, 1, 0, and then we have a weight of minus 1 times that is 0, 0, minus 3, minus 1, 0, 1. And now you see that there's no other way than introducing fractions here. So we have to do row 2, half row 2, and I'm going to also do row 3 already, minus 1/3 row 3. Because I need ones in this pivot. I have the pivots, right? I'm in diagonal form already, but not in echelon form because there are no ones yet. So now I will be, so this is what I get. Divide by 2 is a half, 0, a half, 0, and divide by negative 3, that would be 1/3, 0, minus 1/3. Okay, so we see, because we have 3 pivots, that the matrix is indeed invertible. In fact, at the previous stage, at this stage here, we could actually find the determinant. Because we have this matrix here is in diagonal form, in upper triangular matrix, and we know that the determinant is the product of the diagonal elements. Okay, so we know that the determinant here is 1 times 2 times minus 3, so determinant is negative 6. Okay, we don't need this at this point, but I just want to point it out here. Okay, so we are not done because we have to make zeros in the last column on top of that one. So the 2 more operations I have to do is row 1 minus 3 times row 3, and row 2 minus a half times row 3. So we get 0, 1, 0. So I'm doing this minus 3 here, so that's 0. Minus 3, that's minus 1 plus 1, that's 0. Is 0. Minus 3 minus 1, so that's 1. And then here I do now minus a half and add up to there. So it's 0, 1, 0, minus 1/6, a half, and 1/6. And then the last one, we don't do anything. And so here is our inverse. Now we can check that this is the inverse. Okay, so that's the method of row reduction. Now, how is the adjoint method? If you do the adjoint method? If you do the row reduction method, this is what I need to see. If you decide to do the adjoint method, I'll show you what I need to see. I need you to calculate all C11. Well, let me not put them all too close together. C11, C12, C13. Okay, so what are these? Well, remember, these are the cofactors. So the C11 is a cofactor of the 1, 1 element, so that is basically the factor here. Now there is also a sign, okay? So in this case the sign is plus, so we have 2, 1, 0, 0, right? So 2, 1, 0, 0. Okay, so let me get rid. Oh, no, this is not what I wanted. But I just before we forget about this, let me put the pluses and minuses here. Plus, minus, plus, minus, plus, minus, plus, minus, plus, right? So let's do C12. C12 corresponds to the first element, second row. So first row, second column. I don't know what I said. This is what it means. I see 0, 1, 1, 0. Okay. So, and then, but it's with a negative, so I forgot the negative. Sorry, I got a little bit, let me write this a little bit better. There's a negative here, so I'll do this, show you the negative, that comes from the sign there, right? So, and this was C12. And then C13, that is row 1, column 3, 1, 3, right? And I've left 0, 2, 1, 0 with a positive sign now, so that's the need no sign. Okay, so let's work this out. What is this now here? This is 2 by 2s, we just do the formula, right? So this is 2 times 0 plus 1 times 0, so this is 0. This is minus 0 minus 1, and this is 0 minus 2. Okay, so this would be just 1, and this would be negative 2. Now, we have to do 3 more. I'm not going to do all of them, but we do the same for the second row and the third row. But that's not the only thing. We also need the determinant of A. Now, again, we can, in this case, you could have expanded the determinant along, so we could have done, to tell them, we could do, just give me 1 sec here. I can expand along the row 3, yeah, row 3, because this row here, all right, there's only one cofactor, and I would find that the determinant is 0, 3, 2, 1, that is negative 6. Okay. I could have used my row reduction, because as I mentioned here, after one stage I already got also what the determinant was. Okay. So, and now what is then the inverse? Well, first of all, that's what the adjoint is. The adjoint is obtained by putting these guys and then taking in their spots, so 0, 1, minus 2, but then take the transpose. That's the adjoint, and then the inverse, so A inverse, was you divide now by the determinant. So the adjoint of A, that's this. So this would be now, we said this was negative 6 minus 1/6, and then the transpose is 0, 1, negative 2, and then of course I didn't fill in these things, so I'm not going to do that. But so there are 6 more elements to calculate. That's why I'm saying this adjoint method is quite a lot of computation. But you see, you do get the first column here. You get 0, minus 1/6, and 1/3. And then 2 more columns here that I calculate. And this corresponds to what I just found. Okay. But if you want to do the adjoint, you have to show all this. I mean, all this meaning that including the 6 things that I didn't show, right? But I didn't want to spend too much time on that. So I think inverse matrix is much easier doing row reduction, and sometimes we get the determinant for free from there as well. Not always, but very often. Okay, that's all I want to say about the adjoint, about Cramer's method. Right, Cramer's method. So remember, Cramer's method is to solve a system of equations in which the matrix is a square matrix and invertible matrix. So for instance, suppose that we have a system of equations that is given again by this matrix. So that would be x plus 3y, and I'm going to just come up with some numbers here equal to 1, then 0, 2 times, I'm looking at the second column, 2 times, no, x, y, and z, so 3z here. Sorry. So it's 1 times x, 0 times, okay, I'm getting I should not make too many drawings on my matrix, otherwise I'm lose it. Okay, so the first one is x plus 3 times z equals 1. The second equation is 2y plus z equals, I'm going to make up, these numbers that I'm making up, let me write them in a different color. I'm just making up numbers. Say this is negative 3, and here I'm going to take 4. And what is the equation? Well, the equation was x equals 4. Now, of course, this is a rather silly equation because we have already x equals 4. But just to show you what is it that you have to do, what you have to do is, well, first of all, you have to calculate again the determinant, which we have either this way or that way. But then, for instance, to find what is x, well, you take the original matrix. Let me write down the original matrix. Why this? Jesus, this happens, and I don't know why it freezes sometimes. So the original matrix was 1, 0, 3, 0, 2, 1, 1, 0, 0, right? So now you replace this, to find x, that's the first variable, you've replaced the first column. So this column here, I'm going to replace by these numbers. Okay, so what I wrote down was not correct yet. Yeah? So I'm going to just do this now. So what do I get here? I get 1, -3, 4. And then I calculate this determinant, but I have to divide by the determinant of a, which was -6, right? That's how the formula works. I mean, go look up the thing. I'm just showing you the calculation. You have to, if you want to review it, then go look at the video. Okay, so we have to calculate this. Now I can expand along the row 3 here, because we have this 4. So plus minus plus, so it is a 4, and what is left is 0, 3, 2, 1, and I have to divide this by -6. Right, okay. And so what is the result? Here we see that this 4 times 0 minus 6 divided by -6, so actually the answer was 4. Now, that's true, right? X is 4 because here it says that X is 4. It's a silly, I was silly example. Of course, in the normal case, you cannot read of the thing. But you see, you can find this. So if I ask Cramer's method, I might do this. I might give you a system of equations, perhaps even 4 by 4 or something like that, and then ask you, find the X value of the solution. That means that you only have to do 2 things, right? You have to find the determinant, because that's always in the denominator, and then you have to calculate this first determinant. That's for the x, and for y, of course, you replace the second column by the constants, etc. Okay. Again, because it's a lot of the determinant calculations with determinants. Okay, that's the review for chapter 2. Then, as I said, chapter 4. So this is that. Chapter 4, you have a review. Chapter 5, I also talked about, gave an overview over base of eigenspaces and so on, so I'm going to not do this part, but I want to say something about diagonalization. So the issue of diagonalization, we have seen 2 different things really, and perhaps it's good to put them next to each other. We have, in general, if you have this is by square matrices, this is also for square matrices. And we have seen that a matrix is diagonalizable. It means that if there exists an invertible matrix, P of the same size, and a diagonal matrix, D, such that P inverse A, P equals D. Now, the deal is that D is uniquely determined by A. The matrix P is not. Depending on how you do it, you can have different matrices. Different matrices can give the same result. Okay, that's the first thing to observe here. But the D is always the same, except for the order in which you put the diagonal elements. So the diagonal matrix is the same except for the order in which you put the diagonal, the eigenvalues, because that's are the eigenvalues. But the issue is that it's not always, it's a condition, not always is a matrix diagonalizable. And the only case in which we can run in such a situation is that when you have an eigenvalue that has a higher multiplicity. Let's say it comes in twice in the characteristic equation, but you actually only find one basis factor. Okay, that is, in other words, if the dimension of the eigenspace does not match the multiplicity of the root. So you just see that this can happen even in 2 by 2. So look at this one. So let's look at 2, 1, 0, 2. So a question could be, is A diagonalizable? And if so, if yes, do it. Okay, that could be a question. So here's an example. So what do we need to do? Well, I go quickly over the steps, right? We need the characteristic equation. We need the eigenvalues themselves. So we get 2 minus lambda, 1, 0, 2 minus lambda. Hopefully by now everybody is gotten used to finding quadratic equations, and be very, very careful with the quadratic equations, of course. If you don't mess up with that and you get the wrong equation, therefore the wrong eigenvalues, nothing works. Okay, so we can expand. It's a diagonal, it's an upper triangular matrix or whatever you want to do. It's 2 minus lambda equals 0. So here is exactly the case that lambda is 2 has multiplicity 2. Multiplicity 2, meaning it comes twice as a factor into the characteristic equation. Now, let's see, what's the step 2 is the eigenspace. Now there's only one eigenspace, namely for lambda equals 2. Alright, so how do we do this? We remind you very quickly, we put lambda equals 2 in here, and then we find the null space of the corresponding matrix. So that is 0, 1, 0, 0. Now, look at that, it's already there, so we can analyze everything. We have one pivot variable, that's x2, therefore the other one is a free variable, and we know already what the dimension is. We know that the dimension of the eigenspace is equal to the number of free variables, and that is 1. But that's not good enough because multiplicity is 2. Let's write it down. Let's just work out what it is. What is the solution? Well, a free variable is equal to itself. x1 is a free variable, so x1 is equal to itself. This equation tells me that x2 is 0, so we have x1, 1, 0. So we have only one basis vector. That's what I was saying, right? The dimension of the eigenspace is 1. But we needed 2 in order to build our P. So this is an example of non-diagonalizable matrix. Okay, so let's look at a different example. Let's do 2, 1, 1, 2. Okay, let's do this one. Step 1, the characteristic equation. It's 2 minus lambda, 2 minus lambda, 2 minus lambda, 1, 1, 2 minus lambda equals 0, right? So expanding this, it's this guy, so that would be lambda squared minus 4 lambda plus 4 minus 1. That's lambda squared minus 4 lambda plus 3. And so that would be lambda minus 1 lambda minus 3. Right? It adds up to negative 4, multiplies to 3. And so we have two eigenvalues. So step 2, eigenspace for lambda equals 1. We plug in 1, they get 1, 1, 1, 1. Right? So we put in 1. Lambda equals 1 in here. I think everybody knows this now, so I shouldn't go too long on this. It's almost right away, right? We do row 1, row operation, row 2, minus row 1. I'm giving simpler examples than I warn you. I'm doing a bit simpler examples than you actually will get. You might, instead of 2, 2, but you wanted 3, 3. Okay? But I just want to give you all the features that happen. Okay? So we have 1, 1, 0, 0. We analyze by saying, okay, this is the pivot variable. And then therefore the other one is the free variable. And this tells us that x1 is negative x2, and x2 being the free variable is equal to itself. So we get x2 minus 1, 1. Okay, and then this is eigenspace lambda equals 1. What about eigenspace, what was the other guy? Lambda equals 3. So now we put in 3 in the lambda equals 3. So we get minus 1, 1, 1, minus 1. It's almost as easy, or perhaps if not easier. Jesus, I don't know why it keeps freezing. Okay. So we do row 2, plus row 1 now. Minus 1, 1, 0, 0. Oh, we have to, okay, that was silly. I have to now also do row 1 minus row 1, right? Yeah, let me do it correctly. I should have done that first. Okay, let's do this correctly. first make a 1, then go make the zeros, okay? Let's follow the recipe as we have always been giving it. So it's 1 minus 1, 1 minus 1, and now we do row 2 minus row 1, and that is 1 minus 1, 0, 0. So this is x1, and this is the free variable is x2, so x1, x2. We see that x2 is equal to x2, x1 is equal to x2 from the first equation, and from the second equation we get x2 is just equal to, no, sorry, there's no second equation, I misspoke. The first equation says that x1 is equal to 2, and x2 is a free variable, is equal to itself. Okay, so we get the 1, 1. Now what do we do with these guys? Well, we know what P is. P is obtained by putting these basis vectors, so these two basis vectors as columns, and D is a corresponding diagonal matrix with the corresponding eigenvalues 1 and 3. Now we need to also find the inverse of P. Now by 2, of course you are allowed to use the formula, right? And the formula was, I keep always forgetting it, what is it? We switch the diagonal elements and we make minus the odd diagonal elements, right? And then divide by the determinant. So we first have to find the determinant here. So what's the determinant of P? That is minus 1, so negative 2, so minus 1/2, and then we do the matrix. What is it? We switch the diagonal elements and make negatives of the other guy, and we get this. That's the inverse. Of course, you could also use the row reduction method that I gave. Yeah, I didn't mention this, of course, here when we talked about inverses of matrices. There is one technique for the 2x2s. That's just a formula, which, by the way, is actually not a new technique. It is really adjoints. It is just writing out what it means in a 2x2 matrix to be the adjoint. Okay, so and this now, so this means that P minus pi inverse A, P is equal to D. That's guaranteed to happen. So this is diagonalization, and so we show that this particular matrix is diagonalizable, but what is orthogonal diagonalization? Well, orthogonal diagonalization applies only to symmetric matrices. So this applies to any matrix. For instance, this is not a symmetric matrix, right? It also can apply to non-invertible matrices, right? That has nothing to do with it. Now this is a symmetric matrix. So I could have actually asked a little bit more here. In the second example, could ask what is the orthogonal diagonalization? So what is the difference? So orthogonal diagonalization. So what is the difference is that the P is now even more restrictive. In order to find P, we need to normalize the basis vector. Some of you forgot to do this sometimes in quizzes. Normalize the basis. So we had the basis, the first basis was minus 1, 1, right? And what is the norm of this? Well, that is the square root of minus 1 squared, that's 1 plus 1, that is the square root of 2. So the basis, therefore, the normalized basis would be minus 1 over radical 2, 1 over radical 2. No need to rationalize, okay? The other basis was 1, 1, right? And these are the bases, right? These two columns are the bases, okay? So we had 1, 1, and so this is radical 1 plus 1, that is radical 2 again, and therefore our new basis vector, or rather the unit vector, or the normalized basis vector is 1 radical 2, 1 radical 2. So the P that we should have taken if we want to do orthogonal diagonalization is this. Okay, and what does this mean is now that this is now an orthogonal matrix. What does this mean? That if you want to calculate its inverse, it's equal to its transpose. So in other words, it would be the transpose of this matrix, but look, the transpose of this matrix is the matrix itself, right? Because it itself is a symmetric matrix. Things like that can happen. So I get minus 1 radical 2, 1 radical 2, 1 radical 2, 1 radical 2. So this shortens the calculation of the inverse, right? Because here I had to do something, which I don't need to do now. That's the advantage sometimes of this method. Okay. Okay, what else do I want to say here? Right. Yes. Quadratic forms. I want to say something about quadratic forms. Now, give me a sec here. Oh yeah. Okay. Yeah, that's correct. Okay. Yeah. Okay. Yeah. Oh, sorry. Yes. Okay. That's what I. Sorry. Now I remember what I wanted to say also. An application of this orthogonal of this diagonalization, whether orthogonal or not, it doesn't matter, is that you can calculate, for instance, what is a to the fifth, or let's do a to the fourth. I don't want to get too big numbers here. Okay, so remember we started from this equality here. Whether we use the orthogonal p or we use the original p, I guess I should make them in two different colors to show you that, to indicate that we are two different ways of solving it, right? So this is my new p here now. It's minus 1 radical 2, 1 radical 2, 1 radical 2, 1 radical 2. So we have two different things. We can do either the blue one or we can do the green one, okay? Now, whichever we use, we start from this formula here. And this formula, if we solve for a, that means we multiply with p on the left and with p minus inverse on the right, we get that a is p dp inverse, and then a to the fourth is p d to the fourth p inverse. Okay, I'm just working it out because sometimes people get confused where the p goes and where the p inverse goes. And so what is d to the fourth? That is, so we have p. What is d to the fourth? Well, that d is always the same. It's 1, 0, 0, 3, right? That is 1 to the fourth. Because it's diagonal matrix, you take the 4 powers. This is not how you take a to the fourth. You don't take 4 powers of the elements, of its entries, because that's not correct. But if a diagonal matrix is correct, so we have to do 3 to the fourth, that is 81, p inverse. Okay? Now, as I said, it doesn't matter which your p is, either way will work. If you do the blue p, then it's simpler to, if the problem is like this, it's simpler to use the blue p because then you have immediately the inverse because of the transpose thing. Let's do it that way, okay? So I'm going to use the blue one. So I have minus 1, 1, 1, 1. Now I'm being clever and take out this radical 2 because it's a common factor, 1 over radical 2. That's the p, right? Then we have d to the fourth, which we just said was 1, 0, 0, 81. And then we have p inverse, but p inverse was actually equal to p. And so we have another 1 over radical 2, minus 1, 1, 1, 1. And the 1 over radical 2, 1 radical of 2, we can combine them. And so we get 1 over 2, and 1, minus 1, 1, 1, 1. And now multiply these two matrices, that is minus 1, 1, 81, 81. And now we can work out the next product. That is 1 plus 81, that's 82. Then is minus 1 plus 81, that is 80. Then you get minus 1 plus 81, that is 80. Good thing it's symmetric, right? That's one thing that I have to get here. I have to get a symmetric guy because I started from a symmetric guy. And then the last one is 1 plus 81, so 82. And actually, 1/2, I can actually calculate everything. This is the 4th power of this matrix. Now, if you had to do this by hand, this would be horrible, okay? But I used the blue p, but if you use your original green p, that's fine too, right? And it's perhaps in this case it was simpler because the p itself was much, you didn't have to deal with the radical. That's the advantage. The disadvantage is you have to calculate the inverse by hand or by whatever method you want to. Okay, so that's the application, and then the last one is quadratic forms. Quadratic forms, the only complication is because it is the same as the previous calculation with orthogonal matrices, is that you have to actually come up with the matrix. So very, very quickly an example in two variables again. As I said, I make it sometimes a bit too easy. 3x squared plus 4xy. So what is A? I don't think nobody had problems in finding A, although some make mistakes, but it's more a mistake than finding what it is. That's the, so xy, right? So this is a y, this is an x. The x squared is 3. What is the y squared? There's no y squared, so that is 0. Okay, there's no y squared is 0. So where the xy's go, well, there's an xy and an xy here, but we have to equally divide it, so 2, 2. Okay, so this is our matrix. It has to be symmetric, right? So step 1, characteristic equation. We do 3 minus lambda, 2, 2 minus lambda. That is minus lambda times 3 minus lambda minus 4. That is minus 3 lambda plus lambda squared minus 4. So this seems to be lambda plus 1 times lambda minus 4, add up to negative 3. Yeah, so let me write it this way, because so it has to add up to negative 3. Yeah, make double check, and normally I promise you, I'll never give you weird eigenvalues, so there should be nice numbers, and then you could easily check and double check. And wait, there's actually a way to check it. Well, if your next calculation doesn't give you at least one free variable, wrong eigenvalue. Okay, so this is for lambda equals negative 1, oops, plus 1 means that, okay, I should have written that, right? So here lambda is negative 1, this means lambda is 4. If lambda is negative 1, so I'm subtracting 1 means I'm actually adding, so I get 4, 2, 2, 1. I'm going to do row 1, 1/4 of row 1. I get 1/2, 2, 1. Then we do row 2 minus 2 times row 1. 1/2 minus 2 times, then 0, and that's also 0, of course, yes. No, the first, so this is x1, it's x2 is the free variable, so x2 is equal to itself, and what is x1? Well, by this it's minus 1/2 x2. So we have minus 1/2, 1. Now, in this case, we don't have a choice. We have to normalize. In quadratic forms, you need to normalize because the matrix that you're looking for, the P that you're going for, that's the matrix that gives the substitution of variables, the change of variables, that matrix has to be an orthogonal matrix, otherwise it doesn't work. Go look at the reason why it was orthogonal, why it needed to be orthogonal. So we have to find the norm of this matrix. Now, I don't like fractions, so instead of that, I'm going to take x2 equals 2 and take therefore minus 1, 2. It doesn't make a difference at all, I told you this. You can do this first and then find the norm. Although you have to divide, some people get really confused because you have to divide by a fraction and then they get completely confused by what happens. So let's do it this way, minus 1, 2. What's the norm of this guy? Well, it's 1 plus 4, that is radical 5. Okay, so our basis factor is, so the real basis factor is 1 radical 5, 2 radical 5. Okay, and then the second eigenvalue was lambda equals, so was it 4? So now I'm subtracting 4 from the diagonal, I get minus 1, 2, 2 minus 4. Row 2 plus 2 times row 1. Do it again. Let's do it in order. Let's get first the 1 there and then. So row 1 minus row 1. One negative 2, 2 negative 4, and now I do row 2 minus 2 times row 1. 1 negative 2 and 0 0. Okay, so we have x1, the free variable, minus 2 x2 is the x1 is the pivot variable, x2 is the free variable, so we get x1 x2. 2 times x2 x2, so x2 times 2 1, and we have to normalize. I told you we need this normalize here because we need an orthogonal matrix. That is square root of 4 plus 1, the square root of 5. Okay, So our basis vector now is 2 radical 5, 1 radical 5. And therefore, what is P? So that's step 3 if you want, or whatever, I forget now what step we were. P is these two vectors that we just found, minus 1 over radical 5, 2 over radical 5. And then we have 2 radical 5, 1 over radical 5. Notice that this is again symmetric. That's just, well, coincidence is a big word, but it often happens, but it's not necessarily the case, okay? So P here is, that's P and D is minus 1, 4, right? Minus 1, 4, yeah. The diagonal matrix minus 1, 0, 0, 4. So if we do y equals p times x, this transformation, then we get the new form is this, or the coefficients of the new form, that is minus y1 square plus 4 times y2 square. Okay, this is how the new matrix looks like. Now remember, this is y1, this is y2, this is y1, this is y2. And this is the transformation P. Okay. That's quadratic form. So but each of these topics I have already reviewed videos for, and you can look for more problems in the homeworks. And so make sure that you look at all these reviews and look at the quizzes and all that, and use all this information to prepare yourself for the quiz, the next quiz. And I said, so there will be 4 questions about these topics here. You can kind of guess a little bit one of each chapter. Sounds something like that I might do or might not do, but you know. Okay, all right. So that's it.